Powdered milk, so ubiquitous in our kitchens, recipes, and everyday products, seems like a common, almost obvious ingredient. Yet behind this seemingly light and simple product lies a gigantic, technologically advanced, and incredibly precise industry. Powdered milk is obtained by removing almost all the water from liquid milk using advanced industrial processes, such as spray drying. Every year, more than 9 million tons of powdered milk are produced and consumed worldwide. And the American continent plays a central role in this colossal industry. In North America, the United States is one of the largest global producers of skim and whole milk powders, thanks to massive dairy operations, as well as highly automated processing plants. Across the border, Canada maintains a strong position with a tightly regulated dairy sector and a growing export market for high-quality milk powders. Consumption levels vary widely across the continent. In the US, per capita consumption of powdered milk remains moderate, often between 300 and 500 grams per year, primarily used in industrial food production. But how can a fresh, delicate liquid, stored at only 39.2 degrees Fahrenheit, be transformed into a stable, dry product capable of being preserved for over a year and transported around the world without losing its nutritional qualities? To understand this, we must go back a long way in history. In 1832, Nicolas Appert, a French inventor known for his work on food preservation, developed a method for condensing milk. A few years later, in 1855, the first attempts at drying milk with hot air appeared. But it wasn't until the 1860s that the first commercial productions of powdered milk emerged. These early powders, not yet perfect, were intended for soldiers, sailors, and travelers, as they were easy to transport, had a long shelf life, and avoided spoilage. The year 1867 marked a historic turning point when Henri Nestlé developed a milk-based flour made from evaporated milk, flour, and sugar, designed for malnourished babies. This product was a phenomenal success, saved thousands of lives, and laid the foundations for the modern powdered milk industry. However, the real revolution came at the beginning of the 20th century, around 1920, with the invention of the spray dryer, better known as the spread dryer. This machine sprays condensed milk into a giant tower filled with hot air, instantly transforming the liquid into powder. This extremely efficient process finally made it possible to produce powdered milk on a large scale, with consistent quality and excellent shelf life. During the World Wars, this innovation became indispensable. Light, nutritious, stable, and inexpensive, milk powder feeds soldiers on every continent. After conflicts, it has become an essential product in infant nutrition, humanitarian programs, the food industry, and homes worldwide. But before being ground into powder, milk must be produced, collected, and processed according to strict standards. In France, Brazil, New Zealand, and the United States, large dairy companies impose rigorous standards for animal welfare, product quality, and traceability. Dairy cows often belong to productive breeds such as Holstein, Jersey, Montbéliarde, or Girolando, capable of producing between 30 and 35 liters of milk per day, sometimes more on the most efficient farms. To achieve these production levels, the animals receive a balanced diet, generally composed of grass, forage, corn, soy, minerals, and sometimes energy supplements. She also benefits from constant access to clean water, ongoing veterinary care, and a suitable environment, whether it be pasture, ventilated barns, or modern facilities equipped with milking robots. Milking takes place 2 to 3 times a day. Before each session, the teats are inspected, cleaned with a mild disinfectant solution, and then dried. The first few streams of milk are systematically discarded to check their color and odor, ruling out any abnormalities related to infection, such as mastitis. Once the cow is ready, silicone teat cups are attached to her teats. The system mimics the calf's suckling, alternating between pressure and release. The milk travels through stainless steel pipes to the farm's refrigerated tank, where it is immediately cooled to around 4 degrees, 39.2 Fahrenheit, preventing bacterial growth. Transport to the factory is equally rigorous. The driver-collector inspects the milk directly at the farm and never collects milk that doesn't meet established standards. The milk is then pumped into the refrigerated tanker truck equipped with a cooling system capable of maintaining a stable temperature throughout the journey. Upon arrival at the factory, it undergoes a second analysis, this time in a laboratory. This includes analysis of protein, fat, and cell count, verification of the absence of antibiotic residues, adulteration tests, and comprehensive microbiological measurements. Only after validation does the milk pass into the enormous refrigerated silos, some of which can hold up to 2.5 million liters. The first step in the process is the standardization of the fat content. The raw milk, which naturally varies depending on the diet and the stage of lactation, is sent to a centrifuge where the cream is separated from the skimmed milk. The two phases can then be recombined with absolute precision to obtain whole, semi-skimmed, or fully skimmed milk, depending on the desired end product. The entire process is automated and monitored by real-time sensors. Once standardized, the milk must be pasteurized. For powdered milk, the HTST process is generally used, which heats the milk to 167 degrees Fahrenheit for 20 seconds. This eliminates potentially harmful microorganisms while preserving nutritional quality. After pasteurization, the milk is sent to the evaporators. These gigantic machines operate under vacuum, which reduces the evaporation temperature and prevents any alteration of the milk. Between 50 and 60% of the water is removed, resulting in a smooth, concentrated milk, closer to condensed milk than liquid milk. This concentrate is then sent to the most spectacular stage of the process, spray drying. In a drying tower that can exceed 30 meters in height, the condensed milk is sprayed into a fine mist using pressure nozzles or rotating discs that spin at up to 20,000 revolutions per minute. A powerful column of hot air, often between 302 and 392 degrees Fahrenheit, then passes through the tower. The heat causes the water to evaporate instantly, leaving behind only microscopic solid particles. These particles slowly fall to the bottom of the tower, where they are collected, vacuumed, and transported to cooling systems. The powder is then sieved to remove clumps, homogenized to achieve a consistent particle size, and then transferred to the packaging machines. Depending on the end use, the powdered milk can be packaged in 25-kilogram industrial bags for food companies or in metal tins, and 200 grams to 2-kilogram pouches for home consumers. The packaging rooms operate in a controlled atmosphere to prevent any contamination. Before the packages are sealed, nitrogen is injected to displace oxygen, preventing oxidation and significantly extending shelf life. The boxes are then hermetically sealed, weighed, labeled, inspected by camera, and then sent to the warehouses. The products can then be distributed to supermarkets, shipped abroad, used in the manufacture of chocolate, cakes, and ice cream, or sent to humanitarian programs in crisis-stricken regions. Thus, behind every spoonful of powdered milk you pour into a coffee, a pastry, or a baby bottle, lies a vast industrial chain combining agricultural expertise, scientific research, technological innovation, and some of the strictest quality standards in the world. If you enjoyed this documentary, please like, subscribe, and turn on notifications so you don't miss any of our content. And tell us in the comments. When you see all these ultra-controlled steps, do you find powdered milk a reassuring product, or is it too processed? And in your opinion, is powdered milk better, worse, or exactly the same as liquid milk in terms of quality? We want to know your honest opinion on these questions. But don't leave yet. That's not all. The rest of this video will be just as exciting. So stay with us until the end. Cement is much more than just a material. It's the glue of modern civilization. It's found everywhere. In roads, bridges, skyscrapers, tunnels, dams, and even in the humblest homes. It's used to bind bricks, stones, and blocks together, forming the basis of mortar and concrete, the latter being, after water, the most widely used substance on Earth. In this video, we'll delve into the fascinating process of cement manufacturing, from open pit quarrying to bagging the finished product, exploring the invisible chemistry hidden within giant kilns. We'll also discover its millennia-long history and the revolution it sparked in the construction industry. Before we begin, don't forget to like, subscribe, and turn on notifications so you don't miss any of our documentaries. The idea of a mineral binder is not new. The first civilizations, more than 5,000 years ago, already used rudimentary mixtures capable of solidifying structures. The Egyptians, for example, combined clay, straw, and gypsum to create sun-dried bricks, which were used to build their homes and temples. But it was the Romans who perfected this art. Between 200 BC and 100 AD, they mixed lime with volcanic ash and fine sand. This mixture formed an impressively strong binder called opus cementitium, from which the word cement comes. The structures they left behind, such as the Pantheon in Rome and the aqueducts of Segovia, still stand today, a testament to the effectiveness of their technology. Their monumental domes and vaults still rest on this cutting-edge engineering material. However, it wasn't until 1824 that modern cement was born, when an English mason, Joseph Aston, patented Portland cement. Its name comes from the resemblance between the color of hardened cement and that of Portland stone, quarried on the south coast of England. This marked the beginning of a new era for architecture and industry. All cement begins its life in rock. The main ingredients, limestone, clay, sand, and iron ore, come from massive quarries, often located in the immediate vicinity of the plant. The choice of site is strategic. It must minimize transportation, since every ton of material moved costs time, fuel, and energy. The extraction begins with a spectacular scene, a controlled detonation, drills piercing the ground to a depth of several meters. The holes are then filled with ammonium nitrate-based explosives, carefully measured to fracture the rock without pulverizing it. The entire assembly is connected by a network of cables to the main detonator. A few seconds after ignition, the mountain rumbles. The ground trembles. A perfectly calculated explosion releases up to 200,000 tons of limestone in a single blast. The blasted blocks are immediately loaded into gigantic mining trucks, each with a capacity of approximately 60 tons. Hydraulic excavators equipped with 12 cubic meter buckets can lift up to 17 tons of stone with each movement. These rocks, destined to become the base for cement, then begin their long journey to the factory. The first industrial step consists of reducing the size of these blocks of rock. The trucks dump them into a primary crusher, a massive machine equipped with hardened steel hammers or jaws. Under impact, the blocks break down into pieces the size of a tennis ball. This operation, called primary crushing, facilitates handling and homogenizes the material. The stone fragments are then transported by conveyor belts to the storage area, where they are stacked in alternating layers in a pre-homogenization process. The aim is to standardize the chemical composition of the materials from different quarry faces. Then comes the dosing. Automated systems, controlled by the central laboratory, precisely weigh and mix limestone, clay, iron ore, and sand according to the chemical recipe of the desired cement. This calibrated mixture is sent to a roller mill or ball mill, where it is finely pulverized into an extremely fine gray powder called raw meal. This raw meal has a carefully balanced chemical composition. It consists of approximately 75% calcium carbonate, 20% silica, and small amounts of alumina and iron oxide. Once crushed, it is sent to large homogenization silos, where powerful air currents continuously agitate it to ensure perfect uniformity. This is where the magic of chemistry happens. The raw flour enters the preheating tower, an imposing structure several tens of meters high, equipped with successive cyclones. As it descends from cyclone to cyclone, it is swept by a current of hot air rising from the rotary kiln. In a few seconds, its temperature rises from ambient temperature to 850 degrees Celsius. At this stage, the flour undergoes calcination. The calcium carbonate decomposes, releasing carbon dioxide and transforming into calcium oxide, also known as whey. This chemical phenomenon marks the beginning of the mineral's transformation. The prepared material is then introduced into the rotary kiln, an immense inclined cylindrical chamber over 60 meters long, which rotates slowly on its axis. Inside, the temperature reaches 1,450 degrees Celsius, enough to partially melt the rock. It is there, in this incandescent cylinder, that clinker is formed, a lumpy material composed of hard, dense, spherical gray nodules. Clinker was the heart of cement. It was clinker that, once crushed and mixed with gypsum, gave the material its ability to harden on contact with water. To guarantee its quality, the kiln operates continuously, 24 hours a day, all year round. Because a single stoppage would cause the kiln to cool down and the material inside to solidify. When the clinker leaves the kiln, it is still at 1,000 degrees Celsius. It then passes through a grid cooler, where a powerful blast of air lowers its temperature to approximately 100 degrees Celsius. The speed of this cooling is crucial. If it's too slow, the crystals won't form properly, reducing the mechanical strength of the future cement. Once cooled, the clinker is conveyed to ball mills, where it is ground into powder again. But this time, small amounts of gypsum, about 5%, are added to control the cement's setting time. Without this regulator, the cement would harden almost instantly upon contact with water. Depending on the desired type of cement, other additives can also be incorporated. Blast furnace slag, natural pozzolan, or fly ash from thermal power plants. The crusher, a steel cylinder filled with thousands of metal balls, rotates on its axis. With each rotation, the balls cascade down onto the material, crushing it by impact and abrasion. Gradually, the clinker and additives become a homogeneous and extremely fine powder, cement as we know it. Throughout the process, samples are taken for analysis. In the laboratories, spectrometers verify the chemical composition, while mechanical tests measure compressive strength. The fineness of the grind, the proportion of fine particles, and the curing time are also rigorously controlled. Once approved, the cement is stored in large metal silos before being sent to the bagging line. High-speed automatic bagging machines fill multi-layered craft paper bags, which are tear-resistant and moisture-proof. Each bag contains 50 kilograms of cement, weighed with millimeter precision by electronic scales. The bags are then stacked on pallets and wrapped for transport. Cement can also be delivered in bulk in tanker trucks, destined for concrete plants and large construction sites. Today, cement is at the heart of the modern world. Every year, humanity produces more than 4 billion tons of it, or more than half a ton per person on Earth. From Dubai's skyscrapers to China's suspension bridge, from American highways to African dams, cement shapes our everyday environment. But its energy-intensive and CO2-emitting production also raises new challenges. Increasingly, factories are innovating by integrating renewable energy, more efficient kilns, and green cements with a reduced carbon footprint. Thus concludes the long journey of cement, an adventure where stone becomes powder, where chemistry meets engineering, and where humanity transforms raw materials into sustainable architecture. Behind every building, every bridge, every house, lies this gray dust born of fire, time, and human know-how. If you enjoyed this documentary, please like, subscribe, and turn on notifications so you don't miss any of our content.